Have you ever wondered why humans walk on two legs while most other animals move on four? The journey of human bipedalism is one of the most fascinating chapters in our evolutionary story. From ancient fossils to groundbreaking scientific theories, the origins of our upright stance are shrouded in mystery and debate. Now, let's dive into the captivating world of human evolution and uncover the theories that explain how and why we became the bipedal beings we are today. Bipedalism, or upright walking, is argued by many to be the hallmark of being a hominin. Humans are unique among all living primates in the way that we move around. In fact, the striding bipedalism that we engage in, where one leg moves in front of the other, is incredibly rare in mammals, and we are the only living member of that group to move in such a way. With such an unusual behavior comes a suite of very particular and specialized anatomical features. Our skull is balanced directly on top of our spine, a feature that is in part driven by the position and orientation of the foramen magnum, which is the hole at the bottom of the skull where the spinal cord exists. In humans, it is horizontal and anteriorly situated toward the face. We have a curved spine and a wide cup-shaped pelvis with short lilac plates and a large hip joint. These features facilitate the support of the vertical trunk of the body, as well as efficiently transfer weight through to the legs during both standing still and walking or running. Our legs themselves are very long compared to our arms. We have knee joints that can fully extend and lock, and a highly unique foot with a robust ankle region and specialized arcs for shock absorption. We have also lost many useful features for climbing, such as an opposable big toe, curved finger and toe bones, and specialist adaptations in the shoulder joint. This loss of arboreal capability is almost as important as the acquisition of specialist bipedal adaptations, as it points to strong directional selection for bipedal locomotion exclusively on the ground. But this started long before our ancestors even evolved large brains and language, even before they tamed fire or made stone tools. Skeletal adaptations for traveling upright are evident in fossils of the very oldest hominins, members of the human family, which date to between 7 million and 5 million years ago. After the split from the last common ancestor with the chimpanzees, the earliest bipedal hominin we know of is a species named Sahelanthropus chadensis, a chimpanzee-sized species that lived in Chad in West Central Africa roughly 7 million years ago. They had a combination of ape-like and human-like features. Ape-like features included a small brain, which was even slightly smaller than a chimpanzee's, a sloping face, very prominent brow ridges, elongated skull, and forearm bones that still indicate arboreal activity. Human-like features included small canine teeth, a short middle part of the face, and a spinal cord opening underneath the skull instead of towards the back as seen in non-bipedal apes. It is thought this early hominin, one soon after the last common ancestor split between chimpanzees and modern humans, moved in the trees in a style that was most similar to aspects of the way that gibbons in Asia do today, using a combination of climbing and clambering, four-limb suspension, arboreal quadrupedalism, with terrestrial bipedalism. We know it walked upright on the ground because of the forearm magnum, the large opening where the spinal cord exists in the cranium. Unlike in apes or other primates, the forearm magnum in Sahelanthropus chadensis is located further forward or on the underside of the cranium. This feature indicates that the head of Sahelanthropus was held on an upright body, which is associated with walking on two legs. It is from this broad ancestral locomotor repertoire that human bipedalism evolved, and in every hominin that followed, though still retained some arboreal adaptations, all walked on two legs. In the subsequent hominin fossils, you can clearly trace the evolutionary progression towards full bipedalism, culminating in the way we walk today. Aurorantogensis, a hominin from central Kenya that lived between 6.2 and 5.8 million years ago, also exhibited a blend of ape-like and human-like characteristics similar to chadensis, but Auroran is estimated with a slightly bigger brain, about the size of chimpanzees, not smaller. Although it is challenging to theorize the evolution of locomotion from Sahelanthropus chadensis to Aurorantogenensis due to the scarcity of limb fossils for Sahelanthropus, We have enough evidence from Auroran, a crucial discovery from Kenya in 2000. An upper femur shows bone buildup typical of a biped. Other evidence of the limb bones which suggests bipedalism includes the femoral neck, which is the part of the thigh bone that connects the femoral head to the femoral shaft. This shows the outer layer of bone, or cortical bone, is thicker on the bottom of the neck than on the top, indicative of a biped. However, other features like that of the arms bones and curved finger bones suggest it was also well adapted for climbing trees. This indicates that while Auroran definitely walked upright on the ground, it also retained significant adaptations for climbing, spending a considerable amount of time in trees on all fours, or maybe being on the ground when searching for food. This mix of traits from these early humans highlights the transitional nature of early hominins in the evolution of bipedalism. Following Sahelanthropus and Auroran in our evolutionary tree is Ardipithecus, a genus we know far better. This includes Ardipithecus cadaba, who lived between 5.8 and 5.2 million years ago in the Awash Valley, Ethiopia, and Ardipithecus ramidus, who lived between 4.4 and 4.2 million years ago west of the Awash River in Aramis, Ethiopia. Both Ardipithecus species were still only the size of chimps with chimp-sized brains. Cadaba is represented by a few postcranial bones and teeth, with a particularly notable robust toe bone. This never-seen-before toe bone still exhibited an offset grasping feature beneficial for climbing trees, but it also indicates a bipedal push-off capability, suggesting it played a role in propelling the hominin forward during upright walking. This new modernized toe bone was a unique and important step in bipedalism and human evolution in general, and Ardipithecus cadaba is the first known hominin to possess this trait. The younger Ardipithecus ramidus, named different due to its less primitive facial features, is slightly better documented than the cadaba, thanks to hundreds of fossilized bones recovered between 1992 and 1994 from Aramis in the Afar region of Ethiopia. Over 110 specimens from around 35 individuals were found, mostly dental remains, but also some skull and limb bones. Additional remains from 9 individuals were recovered in 2005 from Asduma in northern Ethiopia, consisting of teeth, jaw fragments, and some hand and foot bones. The bones found that indicate a leap towards bipedalism are a robust fibularis longus muscle used in pushing the foot off the ground while walking, the big toe, which was used for pushing off, although it still would have been used for grasping, and the legs that were aligned directly over the ankles instead of bowing out like in non-human great apes, which allows for better stability, balance, and load distribution. However, it lacked foot arcs and had to adopt a flat-footed stance. These would have made it less efficient at walking and running than later humans, and it may not have been able to employ a bipedal gait for long time intervals. The distance from the sacrum to the hip joint on the upper pelvis is shorter than in any known ape, which helps maintain balance and transfer forces from the body to the pelvis during bipedal locomotion. It is also inferred to have a long, almost human-like curvature of the spine, which are also adaptations for bipedality. But the legs were not completely aligned with the torso and were anterolaterally displaced, and Ardipithecus may have relied more on its quadriceps than hamstrings, which is more effective for climbing than it is for walking. These important findings indicate that Ardipithecus ramidus, like Sahelanthropus chadensis, Auroran tugenensis, and Ardipithecus cadaba, was still a facultative biped standing upright on the ground while moving on all fours in trees. These early humans' ability to both climb trees and walk on the ground reflects their adaptability to diverse habitats and changing climates. We'll explore the theories behind this in more detail later in the video. As I've explained, the brain size of these early hominin tell you that bipedalism developed long before any significant increase in brain size, highlighting that walking upright was a crucial evolutionary step that preceded the development of larger brains. Next, we delve into the well-known Australopithecines, a group of early hominins that lived between around 4.4 million to 1.4 million years ago. Among them was Australopithecus afarensis, who lived from roughly 3.9 to 2.9 million years ago. These hominins experienced a slight increase in brain size compared to their ancestors, with brain volumes reaching approximately 450 cubic meters, about 20% larger than that of chimpanzees. Males were notably taller and heavier than females, reaching heights of up to 5 feet and weighing between 45 to 68 kilograms. In contrast, females were around 3.4 to 4 feet tall and weighed approximately 30 kilograms. This species, including the famous Lucy, a remarkable well-preserved skeleton that has provided significant insight into early human evolution and bipedalism. Scientists are confident in the fully bipedal nature of Australopithecus afarensis, supported by the discovery of the Laetoli footprints in Tanzania. These footprints, dating to 3.7 million years ago, show a well-developed arc and forward-pointing big toe, which are consistent with bipedal walking. As mentioned earlier, the hominins before Australopithecus still had flat feet and an offset grasping big toe. Unlike the opposable big toe of other primates and early hominins, which is adapted for grasping, the Australopithecus big toe aligned with the other toes to support greater bipedal locomotion. It provided crucial support and balance during the stance phase of walking. As their foot would have made contact with the ground, their big toe helped stabilize the foot and maintain balance. The structure of their big toe allows for efficient weight distribution across the foot, which is essential for maintaining an upright posture. And lastly, the big toe is vital for the push-off phase in walking and running. During this phase, the big toe provides the final thrust that propels the body forward. The strong, robust structure of the hallux allows it to bear significant force during this action. Acting as a lever, the big toe enhances the mechanical advantage during the push-off. This lever function increases the efficiency of the stride, enabling longer and more powerful steps. The big toe's role in providing stability, balance, and propulsion highlights its evolutionary importance in the transition from arboreal to terrestrial life. Back to the trail, this 75-foot trail was created by 3 individuals, leaving 70 distinct footprints. Computer simulations using data from afarensis fossil skeletons and the spacing of their prints suggest that these hominins were walking at speeds of 1 meter per second or above, matching modern human walking speeds. Other studies have also supported the theory of human-like gait in these early hominins. A fossilized 4th metatarsal bone found in Ethiopia from this species also shows that this forerunner of early humans had a permanently arched foot like modern humans, a key requirement for an upright gait. Other fossils that also show clear signs of bipedalism, including a bicondylar angle, an anteriorly placed foramen magnum, laterally flaring iliac blades, longer femoral necks and heads, and presence of a lumbar curve. Evolution was steering hominins towards a fully ground-based lifestyle, but they were not completely there yet. For instance, scans of Lucy's skeleton reveal she had an exceptionally powerful upper body with long chimp-like arms and fingers. These features indicate that tree climbing was still a significant part of their life. It was once theorized Lucy's chimp-like arms might simply be features she inherited from a tree-climbing ancestor, but no longer really used. But researchers found that Lucy's arm bones were thick-walled, implying her arms were unusually strong. This is a use it or lose it trait. Bone strength is a direct consequence of an animal's behavior, not something inherited. What this means is that Australopiths were equally at home in the trees as they were on the ground. Interestingly, a later Australopith, Australopithecus sediba, who lived in South Africa around 2 million years ago, walked differently to Australopiths who came before. The discovery of a relatively complete Australopithecus sediba adult female skeleton permits a detailed locomotor analysis in which joint systems can be integrated to form a comprehensive picture of gait kinematics in this late Australopith. Researchers hypothesized that this species walked with a fully extended leg and with an inverted foot during the swing phase of bipedal walking. Initial contact of the lateral foot with the ground resulted in a large pronatory torque around the joints of the foot that caused extreme medial weight transfer into the toe-off phase of the gait cycle. These bipedal mechanics are different from those often reconstructed for other Australopiths and suggests that there may have been several forms of bipedalism during the Pleistocene era. Around 2.8 million years ago, a hominin likely descended from the Australopithecines showed further advancements in bipedalism. This species, named Homo habilis, is one of the earliest members of the genus Homo because they are the earliest of our ancestors to show a significant increase in brain size, averaging around 650 cubic centimeters, a lot bigger than all previous hominin species, including the Australopithecines, and it was the first to be found associated with stone tools. Habilis, being intermediate between relatively primitive Australopithecus and the more advanced Homo, appears to be generally accurate. Habilis thrived in East and South Africa about 2.5 million years ago to 1.65 million years ago. Compared to Australopithecines, this species had a more modern pelvic structure. The ilium was more rounded and better oriented to support bipedalism. Habilis also had more advanced knee joints than the Australopiths that were well adapted for sustaining bipedal locomotion. The femur showed a better developed valgus angle, the angle formed at the knee between the femur and tibia, which further helped in maintaining balance. With Australopithecus being the first to have an arched foot, the foot structure of Homo habilis improved further. It was more modern human-like with a stronger arch, which provided better shock absorption and energy transfer during walking. This adaptation allowed for longer distance travel on the ground. They also had shorter arms and less curved fingers, which suggests a reduced reliance on tree climbing and a greater adaptation to life on the ground. But did Homo habilis still live in trees? Or was it the first of our lineage to live a life completely terrestrial? It seems, just like the Australopiths and other previous hominins, habilis still possessed a short body and long elongated arms, possibly suggesting it still continued its reliance on an arboreal environment. Although it would be hard to find, no evidence of fire or shelter buildings is found associated with habilis, so it is thought they may have still resided to trees to keep them safe from predators, or to sleep at night. This is just a hypothesis at the moment, but given the clear arboreal adaptations, it is plausible that they may still have been occasional tree dwellers. We are about 5 million years into our hominin bipedal evolutionary history, when our ancestors decided to descend from the trees. From the time of Sahelanthropus chadensis to Homo habilis, we finally reach a pivotal moment with a hominin that has lost all arboreal adaptations, with a body fully adapted to walking upright for long distances, just as good as we can today. This species was called Homo erectus. Homo erectus marked a significant milestone in human evolution, demonstrating a profound shift towards a fully terrestrial lifestyle, and the first hominin species whose geographic range had expanded beyond a single continental region, with fossils found across its starting point in Africa as far north as Spain to as far east as China and the Indonesian islands. Homo erectus is arguably the earliest species in the human lineage to have so many human-like qualities, the biggest one being the increase in brain size, with maximum estimated range for late Homo erectus's endocranial capacity being roughly 1,200 cubic meters, and thus overlapping with the lower values expected for Homo sapiens. Adults grew to around 4 feet 9 to 6 feet tall and weighed 40 to 68 kilograms. Even their body proportions varied greatly, like ours from individual to individual. Turkana boy, a 1.5 million year old Homo erectus skeleton found near Lake Turkana, Kenya, was tall and slender, like modern humans from around the same area, while the few limb bones found of Peking man, an 800 to 230,000 year old Homo erectus skeleton found in Zhoukoudian Cave, China, indicates a shorter, stockier build. Earlier hominins had important similarities with living humans, like bipedality, arched feet, forward-facing big toes, changes of more modern human-like pelvis, spine, and limb shapes, but the fossils assigned to Homo erectus display a number of new and distinctly modern human traits. Their body and limb proportions were just like ours. From the neck down, apart from a couple of little differences, such as having denser bones, a slightly narrower pelvis, and wider hips, they were almost identical to us. Arm bones, leg bones, torso, feet, knee joints, curvature of the spine were all remarkably similar and fell within the range of modern human anatomy. This strongly supports the view that they were equal to us in their ability to walk and run bipedally. This would have made Homo erectus efficient long-distance runners like modern humans. This capability would have positioned Homo erectus as one of the world's apex predators. They were likely the first hominin to engage in persistent hunting, a method involving the tracking and exhausting of prey over long distances. A study done by the Journal of Human Evolution suggested Homo erectus would be able to persistent hunt for over 5 hours without drinking, despite possible deviations from modern-like heat dissipation capacity, aerobic capacity, and locomotor economy. Such a hunting strategy would have given Homo erectus a significant evolutionary advantage in terms of nutrition and survival. In a way, the evolution of bipedalism reached a significant milestone with Homo erectus, marking a pivotal moment where subsequent hominins adopted a fully terrestrial lifestyle. From Homo heidelbergensis and Homo rudolfensis to the Neanderthals and Denisovans, these species all retained the essential features of bipedalism established by Homo erectus. This adaptation provided a stable foundation for further evolutionary advancement, ensuring that the key attributes of bipedal locomotion were preserved and refined in these later hominins. All thanks to our ancient ancestors such as Sahelanthropus chadensis and Ardipithecus, who decided to come down from the trees to explore life on the ground millions of years ago. As a result of the evolution of bipedalism, humans have achieved remarkable achievements in various domains. Bipedalism has facilitated the use of tools and the development of complex manual skills, allowing for the creation of sophisticated technologies and the advancement of agriculture, leading to the establishment of stable communities and civilizations. It has enabled humans to travel long distances efficiently, promoting exploration, trade, and cultural exchange across vast regions. Bipedalism has enabled humans to excel in a wide range of sports and activities that require balance, agility, and the use of both hands. Running, walking, and hiking are fundamental activities made possible by bipedal locomotion, forming the basis for sports such as track and field, marathon running, and trail running. The ability to stand upright and balance on 2 legs has also led to the development of sports like football, basketball, and tennis, where quick changes in direction and speed are crucial. Additionally, bipedalism allows for complex movement in activities such as gymnastics, dance, and martial arts, where precise coordination and the use of both hands and feet are essential. The capacity to climb and navigate varied terrains has given rise to sports like rock climbing and parkour. Overall, bipedalism has been very instrumental in enabling humans to engage in and excel at a diverse array of physical activities and sports. The upright posture and freed hands have also contributed to the evolution of intricate communication systems, including gestures and sign language, eventually leading to the development of spoken and written languages. Furthermore, bipedalism has supported artistic and creative endeavors, as the ability to manipulate objects with precision has given rise to art, craftsmanship, and architectural marvels. Ultimately, bipedalism has been a cornerstone in shaping human society, culture, and the capacity for innovation and progress. That's 7 million years of bipedal locomotion in hominins with no return to life in the trees. So why was bipedalism so crucial in our evolution? Walking on 2 legs instead of 4 catalyzed significant evolutionary shifts in our lineage. This adaptation enabled our ancestors to explore wider territories and diversify their diets, profoundly impacting the way we give birth and raise our offspring. Bipedalism was foundational to many of the traits that define human uniqueness. So let's get into the theories of why this vital evolutionary change happened. There are at least 12 distinct hypotheses as to how and why bipedalism evolved in humans, and also some debate as to when. The different hypotheses are not necessarily mutually exclusive, and a number of select forces may have acted together to lead to human bipedalism. Here are the leading hypotheses. Savanna-based hypothesis. The savanna hypothesis is a hypothesis that human bipedalism evolved as a direct result of human ancestors transitioning from arboreal lifestyle to one on the savannas. According to the hypothesis, hominins left the woodlands that had previously been their natural habitat millions of years ago and adapted to their new habitat by walking upright. The evolution of an upright posture would have been very helpful on a savanna, as it would allow the ability to look over tall grasses in order to watch out for predators, or terrestrially hunt and sneak up on prey. However, other scientists state hominins had already achieved the bipedal adaptation that was used in the savanna. The fossil evidence reveals that early bipedal hominins were still adapted to climbing trees at the time they were also walking upright. It is possible that bipedalism evolved in the trees and was later applied to the savanna as a vestigial trait. Traveling efficiency hypothesis. An alternative explanation is that the mixture of savanna and scattered forests increased terrestrial travel by early hominins between clusters of trees, and bipedalism offered greater efficiency for long-distance travel between these clusters than quadrupedalism. In an experiment monitoring chimpanzee metabolic rate via oxygen consumption, it was found that the quadrupedal and bipedal energy costs were very similar, implying that this transition in early ape-like ancestors would not have been very difficult or energetically costing. This increased travel efficiency is likely to have been selected for as it assisted foraging across widely dispersed resources. Postural feeding hypothesis. This hypothesis asserts that chimpanzees are only bipedal when they eat. While on the ground, they reach up for fruit hanging from small trees, and while in trees, bipedalism was used to reach up and grab for an overhead branch. These bipedal movements may have evolved into regular habits because they were so convenient in obtaining food. Also, a hypothesis by Dr. Kevin Hunt, a professor from the University of Indiana, states that these movements co-evolved with chimpanzee arm hanging, as this movement was very effective and efficient in harvesting food. When analyzing fossil anatomy, Australopithecus afarensis has very similar features of the hand and shoulder to the chimpanzee, which indicate hanging arms. Also, the Australopithecus hip and hind limb very clearly indicate bipedalism, but these fossils also indicate very inefficient locomotive movement when compared to humans. For this reason, Hunt argues that bipedalism evolved more as a terrestrial feeding posture than as a walking posture. Findings also could shed light on discrepancies observed in the anatomy of Australopithecus afarensis, such as the ankle joint, which allowed it to wobble, and long, highly flexible forelimbs. If bipedalism started from upright navigation in trees, it could explain both increased flexibility in the ankle as well as long forelimbs which grab hold of branches. Thermoregulatory model. The thermoregulatory model, explaining the origin of bipedalism, is one of the simplest theories so far advanced, but it is a viable explanation. Dr. Peter Wheeler, a professor of evolutionary biology, proposes that bipedalism raises the amount of body surface area higher above the ground, which results in a reduction in heat gain and helps heat dissipation. When a hominid is higher above the ground, the organism accesses more favorable wind speeds and temperatures. During heat seasons, greater wind flow results in a higher heat loss, which makes the organism more comfortable. Also, Wheeler explains that a vertical posture minimizes the direct exposure to the sun, whereas quadrupedalism exposes more of the body to direct exposure. Analysis and interpretations of Ardipithecus reveal that this hypothesis needs modification to consider that the forest and woodland environment, pre-adaptation of early-stage hominid bipedalism, preceded further refinement of bipedalism by the pressure of natural selection. This then allowed for the more efficient exploitation of the hotter conditions ecological niche, rather than the hotter conditions being hypothetically bipedalism's initial stimulus. A feedback mechanism from the advantages of bipedality in hot and open habitats would then in turn make a forest pre-adaptation solidify as a permanent state. Provisioning model. One theory on the origin of bipedalism is the behavioral model presented by C. Owen Lovejoy, known as male provisioning. Lovejoy theorizes that the evolution of bipedalism was linked to monogamy. In the face of long interbirth intervals and low reproductive rates typical of the apes, early hominids engaged in pair bonding that enabled greater parental effort directed towards rearing offspring. Lovejoy proposes that male provisioning of food would improve the offspring's survivorship and increase the pair's reproductive rate. Thus, the male would leave his mate and offspring to search for food and return carrying the food in his arms, walking on his legs. This model is supported by the reduction of the male canine teeth in early hominins such as Sahelanthropus chidensis and Ardipithecus ramidus, which along with low body size dimorphism in Ardipithecus and Australopithecus suggest a reduction in inter-male antagonistic behavior in early hominins. In addition, this model is supported by a number of modern human traits associated with concealed ovulation, such as permanently enlarged breasts, lack of sexual swelling, and low sperm competition that argues against recent adaptation to a polygynous reproductive system. Warning display model. Joseph Jordania from the University of Melbourne suggests that bipedalism was one of the central elements of the general defense strategy of early hominids based on aposematism, or warning display and intimidation of potential predators and competitors with exaggerated visual and audio signals. According to this model, hominids were trying to stay as visible and loud as possible all the time. Several morphological and behavioral developments were employed to achieve this goal: upright bipedal posture, longer legs, long tightly coiled hair on the top of the head, body painting, threatening synchronous body movements, loud voice, and extremely loud rhythmic singing, stomping and drumming on external subjects, slow locomotion, and strong body odor, which are both characteristics for hominids and humans, are other features often employed by aposematic species to advertise their non-profitability for potential predators. Carrying model. Charles Darwin wrote that man could not have attained his present dominant position in the world without the use of his hands, which are also admirably adapted to the act of obedience of his will. The carrying hypothesis is one of the most widely proposed theories for why humans evolved bipedalism. This theory suggests that early hominins may have started walking upright to carry more food at once and free up their hands for other tasks, especially tools for defense and hunting. This theory is problematic in that the earliest stone artifacts dated only to about 3.3 million years ago, long after hominins had become bipedal, thus requiring an assumption that earlier tools were made of wood or other perishable materials. Wading or aquatic ape model. The observation that large primates, including especially the great apes, that predominantly move quadrupedally on dry land tend to switch to bipedal locomotion in waist-deep water has led to the idea that the origin of human bipedalism may have been influenced by waterside environments. This idea, labeled the wading hypothesis, was originally suggested by the Oxford marine biologist Alistair Hardy, who said, "It seems to me likely that man learned to stand erect first in water, and then, as his balance improved, he found he became better equipped for standing up on the shore when he came out, and indeed also for running." Other theories have been proposed that suggest wading and the exploitation of aquatic food sources which provide essential nutrients for human brain evolution, or critical fallback foods that may have exerted evolutionary pressures on human ancestors, promoting adaptations which later assisted full-time bipedalism. It has also been thought that consistent water-based food sources had developed early hominid dependency and facilitated dispersal along seas and rivers. Other behavioral models. There are a variety of ideas which promote a specific change in behavior as the key driver to the evolution of hominid bipedalism. For example, Westcott in 1967 and later Jablonski and Chaplin in 1993 suggests that bipedal threat displays could have been the transitional behavior which led to some groups of apes beginning to adopt bipedal postures more often. Others, like Raymond Dart in 1925, have offered the idea that the need for more vigilance against predators could have provided the initial motivation. Evolutionary biologist Richard Dawkins argued that it could have begun as a kind of fashion that just caught on and then escalated through sexual selection, and it has even been suggested that male phallic display could have been the initial incentive, as well as increased sexual signaling in upright female posture. The evolution of bipedalism in early hominins was likely driven by a combination of factors rather than a single cause. It seems unlikely that a single factor was responsible for such a dramatic change in the evolution of bipedalism. Climate changes that led to the reduction of forested areas and the expansion of open savannas might have necessitated a more efficient means of long-distance travel, which bipedalism provides. Additionally, the ability to carry tools and food while keeping the hands free would have offered significant survival advantages, fostering technological and social development. Enhanced visual surveillance from an upright position would have improved the ability to spot predators and prey, further aiding in survival. Thermoregulation also played a role, as standing upright reduces exposure to the sun's heat, helping to maintain body temperature. Energy efficiency, with bipedal locomotion requiring less energy over long distances compared to quadrupedalism, would have been advantageous in the search of food and resources. These interrelated factors probably collectively influenced the shift to bipedalism, demonstrating that it was a multifaceted evolutionary development. If you disagree or have any other hypotheses on why we started to walk on 2 feet instead of 4, let me know in the comments below. And don't forget to like and subscribe if you enjoyed the video. Thank you all for watching. Goodbye.